All right, so hi, my name is Ram Murthy. I'm a principal software engineer here at Keysight Technologies, and the topic for today that I wanted to discuss is how we in Keysight we're building and delivering a P4-based network tester, and not only is it P4-based, but it's also leveraging some OCP-inspired hardware as well. So the goal of the talk is to kind of go through that. All right, so the agenda for the talk is the following. First, we'll look kind of at our motivations in building the solution by examining the existing market trends. Next, we'll focus at a high level on what the definition of a layer 2-3 network tester is. And the key question that we want to analyze is, can we leverage OCP and P4 to implement a network tester? After establishing definitions and context with our introduction, we'll explore a common use case as a vehicle for really understanding what are the building blocks necessary for making a network tester. And then with that understanding of the primitives and the building blocks, we'll take a closer look at examining the compare and contrast between FPGA and P4, as well as OCP hardware and custom hardware. And then finally, we'll kind of correlate that all back into what is the big picture in terms of test and measurement, and what does it mean for the community in general. So let's get started then. All right, so in this slide, we kind of want to examine, the trends that we've been seeing in the industry, and specifically with the advent and proliferation of merchant silicon, we are seeing, the cloud service providers and hyperscalers moving to a more disaggregated and distributed architecture. The proprietary monolithic closed box architectures are moving, as you can see, to these more modular and disaggregated architectures, and this is driving down the cost per gigabit of switch traffic. And this coupled with, the increased bandwidth requirements we're seeing across the industry is really driving 100 gig growth in terms of switch ports. And in the news, we can kind of see, the NEMs are also kind of moving into this model, as well as the hyperscalers in terms of white box deployments. And so the question is for Keysight, how can we best test these solutions, and what can we provide to the community to, really accelerate this? And so here I want to talk about, we recognize that, the Sonic community is already kind of going through this process. The Sonic community has defined this community test bed to run these test cases, and that question is already being answered. And specifically, we're seeing this trend moving from the traditional test gear, very similar to what we're seeing in the switching gear from these monolithic proprietary solutions into a disaggregated approach with OCP inspired hardware. And, for us, the question was, this is the way the community is moving. What can we do to kind of answer the needs there? And so on the hardware side, that's where UHD comes in, where we're again using this OCP inspired hardware and trying to leverage kind of the synergies that are there within the OCP community. At the same time, we recognize, that within the community, the need for choice is important, the right tool for the right job. And so we recognize that, some people may want to use the community test bed and not use UHD, whereas we think maybe in some situations, UHD would be a better choice for a solution. Nonetheless, we're also contributing to the Sonic community, something that we're calling Snappy. And the goal behind Snappy is it's a traffic generator API that we want to be able to run on any of these 3 different testbed solutions, and really behind the open source kind of idea of promoting choice. And so we'll a little bit deeper into what Snappy is here. So like I was showing in the previous picture, Snappy, the whole idea is to be able to run on any kind of backend client that is implementing the testbed. And really the motivation for this comes from the fact that when you look at previous APIs coming from test and measurement vendors, they are very kind of vendor specific kind of functional models where features are mapping one-to-one to features provided by the hardware. And we understand, when somebody is writing a test for, PTF or within the Sonic testbed, we don't want them to have to duplicate their work for that to run on one of our solutions, right? And so one of our contributions that we're trying to make within the community is to define and deliver this open source model for a traffic generator API. And again, we're trying to leverage some of the philosophies that have come in from the open source community. And specifically what that means is to leverage, open API standards, as well as having a declarative model versus what, we've previously done in the past with specific functional models. And so you guys can check it out. It's on GitHub here with the, open traffic generator APIs, as well as pip package that you can install. We actually have a pull request also open in Sonic with using the traffic generator APIs to define a test case there. And so this is kind of like the motivation at a high level. But at the talk, we're really looking at the targeted solution at the hardware level for what we think is going to be good. So let's get into the hardware specifically. So before we kind of dive deep into the implementation details of P4, et cetera, we want to kind of establish the definitions for what a network tester really is. So first and foremost, the main objective of a tester is to measure and characterize network devices and systems. For instance, an original design manufacturer or network equipment manufacturer will be interested in qualifying the throughput, latency, and forwarding correctnesses of their devices prior to shipping or going into production. Similarly, a network operator may be interested in qualifying the routing correctness of protocols such as BGP or convergence performance such as ECMP with a set of devices ready for deployment. Next, we'll pose some critical questions that we faced along this design and development phase. And first and foremost, can we leverage OCP and P4 to make a network tester and really leverage those synergies that exist there? Specifically, can we support our customers' typical use case and performance requirements and create a minimum viable product using these technologies? Along those lines, can we leverage our existing IP and maintain the same user-facing experience while integrating a completely new data plane technology and hardware platform? And finally, what does it really take to deliver this product to market? And what is the best way to accomplish this? So now that we've kind of taken a basic understanding of a network tester and our targeted questions, let's explore a concrete use case to really identify the basic building blocks. Here we'll examine a common test case for network operators, which is to evaluate routing and convergence. In this scenario, the tester will emulate a top-of-rack server as well as a set of top-of-rack switches, typically found in your class topology. Specifically, the emulated switches will advertise BGP routes corresponding to downstream servers. The emulated server will then send traffic over those advertised routes to the Tor switches. And then the tester will then measure the distribution of the flows prior to and subsequent to a failure event, which is a link down event. And then finally, the tester will also measure the amount of time for convergence to occur after the failure event. So let's go to this demo here. So here you can see we have the one tester port, which is sending at 100% line rate, and we have the 8 other receive ports that are receiving that traffic from the tester. Let's start this demo. Looks like I'm having some difficulties here. Oh, come on. That is unfortunate. Essentially in the demo though, dealing with the technical difficulties here, we'll see in the demo that we basically can measure the amount of time that it takes for the convergence to occur. Let me see if I can pull up a previous slide that I had. Or maybe I can get to it back when we get to the questions and I can pull it up. But essentially in this demo, what you wanted to show is, showing a typical use case with ECMP where the tester is going to send, and we're going to basically see at a link down event that traffic gets redistributed and we get the convergence time. But unfortunately, it looks like the video is not working on this slide. So let me continue. So looking at that use case and really looking at the ECMP use case, we can see kind of what we really need at a high level. And, at the high level, we need to have BGP on top of to basically test and advertise the routes. And then we need to be able to precisely generate and analyze the traffic flowing through the system under test. And specifically, you can see here that we need to generate these specific routes, in the flows, and then provide the metrics associated in terms of throughput, in terms of latency, and things like that. Hit the space bar. Okay, I got Mono telling me. Let's see. No, it's not happening. I've got somebody else telling me, but let's continue. I think we'll get back to it and we'll be able to show it. So digging a little deeper into kind of the building blocks, right? We can represent the primitives in a block diagram to really understand what the pipeline is going to be. And at the minimum, the tester needs to be able to send specific packets at a target rate and instrument those packets as needed to analyze on the receive side. The receive side will then analyze those incoming packets and then collect the metrics associated with the flows based on the instrumentation found in the packet. So both on the Ingress and Egress pipelines, we also need to give you statistics in a way that the software can effectively correlate to really show what's happening in the data plane side. So let's get started with the technical details of the implementation. One of the key primitives that we highlighted is the ability to precisely generate the flows that are on the wire that correspond to the routes that are happening within the BGP. So typically in FPGA products, we support this construct of called user-defined fields, which are UDFs. And the UDFs typically can modify arbitrary offsets in a packet. However, this sort of primitive does not really exist in the P4 specification, as the more natural API is really dependent on the header fields found in the parser. So what we really want to go back to is this absolutely necessary. Going back to our BGP use case, we can really see that the fields that need to be modified are things like the layer 2-3 source destination addresses and the layer 4 source destination ports. And so coming back, to what is possible in P4, with the more limited approach, it's pretty simple to actually achieve the use case on the wire. We can maintain an index of, how many packets are in this flow, and we can basically read on that index and populate the packet with the appropriate values that are necessary to emulate the flows on the wire. And so we can see here that, the use case is pretty simple to implement in P4. And so we have that building block, available. The next block we'll examine is the Ingress parsing of a packet signature in instrumentation. In typical FPGA products, the signature can be placed anywhere in the packet. Again, this is a very difficult thing to accomplish in P4 as there's not a clean way to scan the entire packet, including the payload, for the signature. So we can place some additional assumptions here that the signature is always after all of the known headers that the customer is interested in the packet. And this greatly simplifies the problem and allows us to, again, use a match action unit to implement the ternary match for the signature. Coming back to the use case, this is acceptable as the system is not concerned with the payload of the layer 4 packets. They want us to be able to send them along the routes there. As a final block, we want to examine how statistics collection is done. As you can see in our typical products, we've provided the ability to give precise snapshots of the TX rates and RX rates, and that is typically accomplished in FPGA using what we call ping pong RAM buffers. However, in P4, this is very, very difficult to accomplish, and we have to be very clever in terms of the way that we need to do this. And this, again, is trying to highlight some of the trade-offs that happen in terms of P4 versus FPGA. Let's get to the next slide then. So after kind of examining the building blocks, we can kind of see that we have what is available. We have the building blocks necessary to really do it. So we want to kind of get into the other analysis in terms of the hardware side and the development side. So in this section, we're going to try to examine some of the differences in terms of hardware. So typically in test and measurement, we're making custom hardware that is purpose-built to basically generate traffic and analyze. And we really want to analyze the reliability and availability of this. So when we're building custom hardware, we intrinsically have less diversity of vendors in the supply chain just because we're building very specific components. And oftentimes we're also leveraging bleeding edge technology, which inherently has some issues in terms of reliability, in the early phases of the development cycle. And I really want to contrast this with the OCP hardware that we're using now. And what we've been really able to achieve is with this industry standardization that OCP provides, the hardware procurement and reliability is much higher. In addition, the diversity of the vendors allows for much easier procurement of hardware, and there's a lot greater resilience in the supply chain with the many different vendors available to basically create the hardware. In addition, we're able to get prototypes of hardware that are full featured, much earlier in the cycle. And that really, makes the product development cycle much quicker. This is something we really want to highlight in terms of being able to leverage the synergies that the open source community has been able to provide. The next thing I want to kind of analyze on the hardware side is, the cost of it. Typically when we're making custom hardware, we have to obviously design it, and that requires R&D from the engineering side. In addition, we have high prototype costs for early hardware, which does not always have the full functionality. And due to the low volume that we have with the very specific hardware, we tend to get much higher COGS in terms of, the parts that are used in the components. However, we have the trade-offs. We have the ability to make very specific hardware with the customer in mind and the feature spec in mind. And so there are pros and cons to the situation. On the OCP side, we're really able to leverage, the industry standardization. And so we're able to get much lower COGS on the hardware platform. And specifically, OCP provides a common kind of way for the COM express boards, the BMCs, the fans, the power supplies. And due to those higher volumes, we can get a lower product, lower price for a product. In addition, working with the ODMs, we can drop ship directly, which really eliminates a lot of the local costs in terms of expenses in manufacturing. And that's been a real boon to us in our product here. But again, our customization is pretty expensive. We really have to stay within the confines of what the box can provide. And it boils down to really delivering value through software rather than the hardware platform itself. Next, I want to kind of get into a compare and contrast of the technologies at hand, looking at Fpga development versus P4 development. One thing that, is off the bat is pretty clear is that building an Fpga takes much more time. Typically, build times for FPGAs are 3 to 6 hours to route and 1.5 hours to synthesize. And on average, we need 5 Cs to basically build strategies, which can be done in parallel, but introduces more complexity into the build process. And on top of that, we also have to take into account timing and utilization, which it adds additional complexity to the development process. This is in comparison to P4, which can compile the data plane plus the API bindings in about 5 minutes, which is much, much faster. And with this improved performance in terms of build time, it allows for much quicker iterations on the code and compile and deploy cycle. So this really speeds up the development process for an agile development methodology, and we can really go and hit the road running, in terms of the product. Another key thing that I want to touch on in terms of FPGA and P4 is kind of what the interfaces really look like. On the FPGA side, we typically get a register map that is provided in the design documents, and that's typically handed off between a few different teams. So there is that complexity of having multiple people touch, the product in terms of implementing a specific feature. And this is in comparison to P4, where the P4 compiler will automatically generate the APIs for the P4 program. And those APIs can be exercised in a variety of different ways that allow for integration by the same developer. For example, in our workflows, we typically have a single developer make the P4 feature and then basically test the APIs via Python using the gRPC interfaces. And then that integration can then easily happen, with the C APIs or the C++ APIs. And, we can quickly get a feature up and running on the platform in comparison to something we've typically done with FPGA and custom hardware. So there are some benefits here that we can see. So I want to kind of summarize in what our takeaways here. We came in with this motivation of how can we better test this disaggregated solutions that are coming out. We looked at OCP and P4 as a potential way to do that. And so the question was, were we able to accomplish that? And, I would say the answer is a qualified yes. FPGAs are always going to be critical for network tests. And, some key examples that I think are important to highlight is anytime there's a new speed or feed in terms of Ethernet, for example, looking in the future with 800 gig or 1.6 terabit, the solution for test and measurement is always going to be FPGA based because the silicon to implement that is not going to be available in time. Another area that we kind of touched on in terms of custom hardware and OCP hardware is when you have to do really high scalable tests, it's very difficult to achieve that with ODM hardware. And so there's always going to be this market for FPGAs to implement the use cases at the high end. However, in terms of what I can see in the future, there's a bright future in terms of having the synergy in hybrid systems with P4 programmable ASICs, OCP hardware, and potentially some FPGAs in that system as well, where we can, for example, provide features like MACsec or things like that. And in general, I think it's important to highlight that P4 enabled systems based on OCP hardware will spark innovation. We can see that clearly with the project that we've done here with UHD. And then finally, I want to kind of get back to our questions. Through this kind of exploratory phase and questioning of how best can we achieve this testing, we definitely found that we could leverage this with OCP hardware. We were able to take our years and years of IP and kind of plug that in kind of seamlessly into the product. And from a research perspective, we were able to do it fairly quickly by really leveraging the synergies that were provided by OCP. And so we can kind of see here at a high level, we really leveraged OCP and P4 to transform a typical hardware project into a software project. And specifically, we were able to successfully transition to a more modern agile development process with more CI/CD pipelines and the whole gamut in terms of what's happening in the software world today. Finally, I want to kind of have this call to action here. Through this experience, we really can see, the value of taking the synergies that are available in the open source community. And, there's clear value there in terms of open interfaces. And from my side, I believe, as an industry, we must continue to strive for more collaborative and open approaches, which will enable rapid innovation. And as a company, Keysight is very excited to be a contributor to this movement. And we look forward to collaborating and delivering on this vision here. Really in terms of tangible stuff, we have Snappy in the GitHub page, and we're really looking forward to, kind of integrating that into the Sonic ecosystem, because we think the idea of promoting choice is very important here. And so take a look, and feel free to give us some comments and feedback, and even, make your own changes if you'd like. And then finally, I'd just like to, give some acknowledgements to the different teams that were involved in this process. Specifically, I'd like to thank the Keysight team, the development team here that worked on this, tirelessly. I'd also like to thank the Intel and Barefoot engineering and support teams, and their support for everything that we've been doing. And finally, just giving homage to the open source community with OCP and the P4 language consortium and Sonic for working with us. Thank you. Any questions, I guess?
Thanks, Ram. Yeah, we'll wait for some questions. There are none yet, but
all right.
While we wait, do you want to get your demo again?
Yeah, yeah. Let me get that up. Let's see here. All right, I have it here. Okay. Let's, I need to do it here. Okay. So I have it running here. You can kind of see here that oh my gosh, so sorry. So here we can kind of see that the tester is sending, at 100% line rate, and that is being distributed via ECMP to these 8 ports here. And you can see here now that the link has gone down on one of those ports. We should then see basically the system under test redistribute that traffic per ECMP. And we should see that here shortly, where the traffic will go and redistribute. So you can see that here, this port basically has no traffic coming to it anymore, and that the rest of the traffic has been redistributed amongst the remaining ports that are available. Then finally, the tester will be able to basically take a measurement of the amount of time for convergence, and we can kind of see here that the tester has measured a packet loss convergence time of 12.3 milliseconds. And that's kind of the demo there, so basically showing UHD as a system accomplishing one of the more important tests, that network operators tend to run. So that's the demo I had to show there. I'm sorry about the technical difficulties.
No problem. So have there been any contributions already on the way to the Sonic?
Yeah, so if you look kind of back here on this page, let's get back. Kind of posted the pull requests that are, yeah. So we've got a GitHub page here open in terms of, there's some echo there, but I posted, basically the GitHub page, and obviously the success of an API is very much dependent on the community embracing it. And so any kind of commentary there that's, provided by the community would be great. We really acknowledge, in the past, some of our APIs have been very, kind of vendor specific, right? And, within the open source community, I understand, people want to have the ability to choose what they want to run on. And so we really look at, this contribution here as the ability to run, not only on our hardware, but also, on the community test bed. And, we obviously vouch for what the hardware can do in terms of things beyond the community testbed. We definitely think there's performance and scalability that's achievable with UHD, for example, that's not necessarily quite there in the community testbed. We understand at the same time, right tool for the right job. And so if people want to use the community testbed for whatever reason, then we should be able to support that, and we don't want people to write tests multiple times. We really want them to write it once and then just say, hey, I want to run it on the community testbed. I want to run it on this hardware, this hardware. And we want to make it so that people can even add hardware, you know what I mean? Because that's really going to enable choice. That's the biggest thing. When we make things open, we see more innovation happen. And that's really, one of our values here that we want to push forward. I think you're on mute, sorry.
Yeah. So are there any other hardware platforms in the pipeline?
So, we're looking at 400 gig, obviously, that's coming in down the line, waiting for, full availability of all of that. But, that is definitely something we're looking at. And, I'm just looking forward ahead. I definitely see this being a part of our product portfolio as we move forward, with the different chips that are going to enable this. Obviously down the line, this is our first one that we've really achieved. But, once the first one's done, the next one's a lot easier. So.
Yeah. Yeah, the disaggregation part and also the CI/CD, right? Moving into a different kind of development for this is kind of exciting.
Yeah, it was definitely a fun project to be a part of, really just, kind of start from the ground up and look at how can you do things differently. We definitely looked at, a lot of the different technologies too on the software side in terms of Docker and Kubernetes, similar to kind of how Sonic is looking at it, and really have been able to leverage that successfully within the product as well. So, we really believe in kind of the technologies and, the principles behind it, especially, that the idea of, having more modular software and more modular components is going to be important, And so, yeah, it's definitely something that we're reacting to a little bit, but I think it's good that we're embracing it now wholeheartedly.
Yeah. I'm guessing this also enables software functional testing, right? The P4 runtime can be run on a completely software mode. Of course, not at that scale, but
Right. It does, with the models in place. Ooh, lots of echo. Yeah, with the models in place, it does allow for, kind of using that to kind of simulate things. Typically, really what I've seen though is, we've got plenty of hardware available since it's a lot cheaper and people just typically use that. I don't know. So it is interesting to be able to look at running simulations and being able to kind of do CI/CD that way. But we've definitely taken the strategy of let's just throw hardware at the problem at the moment, But yeah, definitely, if hardware is scarce, and especially as we get to, newer chips and things like that, I think, you can leverage that in the early part of the game to really bring up a product,
Yeah. At least testing the control plane too.
Yeah, that's right.
Yeah. Okay. There are no questions on the chat. Thanks, Ram.
Okay.